useful. Today's lecture is going to be useful for that purpose too. Before I start, are there any questions about what we have talked about so far? Any specific questions about the homework assignment? Any questions about structures, pointers, and arguments? What's on the stack? The instructions that we are using at this point. So, any general questions? Okay, I do not see any hands up. Yes, go ahead.
Can you go over the answer homework assignment?
Can I go over the answer? What?
Homework assignment that you're doing?
That's due on Thursday.
No, due today.
Oh, the swap subroutine?
Yeah.
Okay, yes, we can do that. All right, so that means we might need to have to kick into overtime, but I don't have any specific lab activity for you guys to do today, so I can spill over the lecture into the lab time, probably with a short break, so that you guys don't get too tired. All right, so let's go ahead and take a look at that. So we'll go to, I'll sign into Canvas first, because this way we can take a look at your homework assignment. All right. And we go to the Tuesday, Thursday class. Let me, all right, so I think that's just called the function calls. And I'll just do a preview because I need the source code in question number 4, I believe. All right. So we're looking at the C code of the swap subroutine, as well as the provided assembly code in TTP ASM, or the assembly language of text toy processor. So your job is to implement the swap subroutine. So do we have any questions about the C code first? I will copy and paste these into my editor so we can actually see the C code and the assembly code side by side. But I want you guys to kind of take a look at the C code for now and see if you have any questions. So do we have any questions about the C code? Do we have any questions about what this line is actually going to do? Okay, I'm not seeing any questions. All right. All right, so given that is the case, I am going to create the programs in the temp folder. So we have swap.c. I already got that created for the other class like some other day, but I'm going to overwrite all the files so we have a clean starting point for this class. So now we have the assembly code. There are many ways to approach this particular program, and I can describe. I don't have enough time to really describe all of the different ways. It depends. We'll see. So we'll go ahead and paste that in. There we go. So I can now show you both the C code and also the assembly code, and we'll have those two displayed side by side. So one more time, do we have any questions about the C code that is on the left-hand side? So the use of the dereference operator is clear. You guys know what a pointer is and what dereferencing actually means. Very good. Okay. All right, so now we can focus on the right-hand side, which is the TTP-ASM, the assembly code. So the first thing I'm going to do here, you should not do this, in the lab itself, because by doing this, the offset of all the instructions would have changed, and so the answers would not have worked out. Okay, but when you're actually coding it, you would need an no op here in order to use River Spider. I'm not sure how many of you have set up to use River Spider. If you have not, you can still do it manually, which I can also demonstrate as well. So when you write a subroutine in assembly language, the first thing you really want to make sure is understanding what is where on the stack. So everything that is related to swap would be PTR2, which is our second parameter, PTR1, which is our first parameter. We have the return address, which is pushed by the caller. And then we also need to allocate for the local variable t, and that's going to be the last item. So this is where register D points to at the entry point of your swap, and this is where register D or the stack pointer should point to right after local variable allocation. So are we doing okay so far with the picture of what is on the stack when everything is set up correctly? Are we good here? All right. Okay. So now what we need to do, you can do this without these labels. Okay. There are ways to do this without the labels, and it makes it a little bit harder to understand the code, but with the label definitions, it makes it easier to understand what we are doing at any particular time. So I'm going to use your swap underscore t to be 0 because this is exactly where the stack pointer should be pointing to after I allocate for the local variables. In other words, the displacement or the offset of where I can find local variable t is 0 byte away from where the stack pointer points to, and therefore it is defined to be 0. Swap underscore LVS, which is local variable size, is swap underscore t 1 plus. This one here is referring to the size of the local variable t itself, and since it is a 8-bit unsigned integer, it is only 1 byte wide. And then we have swap underscore PTR1. That is going to be swap LVS1 plus. This one here is referring to the number of bytes used by the return address, and that's one single byte. And then we have swap underscore PTR2, which is swap underscore PTR1, 1 plus, and this one here is referring to the size or the number of bytes that we need for PTR1. All pointers within the TTP architecture is only 1 byte, so that's why there's a 1 here. So do we have any questions about the label, the definition of the labels? The labels do not actually do anything at runtime. Okay, they are just assembly time constructs where it allows you as a developer, instead of saying 0, 1, and then 2, 3, and so on, you can now refer to the symbolic name, which means it's easier for you to handle the code because now you don't have to remember what is at what offset from where the stack pointer points to. But it doesn't actually do anything to the stack itself. So that means the allocation and the deallocation of the local variables, they have to be done using instructions that you write into the program. So that's why we need a LDIB with swap underscore LVS, and then we do a subtraction from the stack pointer to do the allocation. And then at the end of the subroutine, we're going to do the reverse in order to deallocate the local variables. And then after that, we can do the usual return code, which is LDBD increment D. This is basically just popping whatever the stack has into register B, but that should be the return address. So that means once we have the return address in register B, we can do a JMP without the I, just JMP B, to continue execution in the caller. So given only this much, I want to check to see if the code is going to work or not. Because if this part is not working, there's no point in inserting any additional code between line 43 and line 45 because the stack is not properly set up or things are just not right. So if I were writing this program, I would just make it run first to make sure that everything looks good, the stack is balanced, everything is going to be okay. So what I would do is I would just go to River Spider to run this. Now, if you do not want to install River Spider, I do understand there are quite a few steps to get it to work. In the end, the amount of time that you're saving using River Spider, I think is worthwhile to follow all those instructions, even though there are a lot of instructions involved. But if you don't want to do that, hey, it's still going to be okay. You can still make it work. It's just a lot more manual steps. So I can demonstrate once of how to do it manually, but it's already described in one of the documents that I have shared with you on Canvas. So what you can do also is to follow those instructions. So because we are running kind of short on time in today's lecture, so I'm just going to use River Spider for now. And the program name is swap.ttpasm, and it goes to the assembler, and it should return with the object code, and it would do the simulation, and it would turn the trace data into the trace raw data sheet, and then the analysis sheet should now have the actual analysis of what happens when this code executes. So we go to the assembler, and just wait a little bit. And what I want to do is to at least go to the end. Oh, this doesn't look good, does it? I must be missing something. Huh. Okay. So something is not working correctly. It continue execution at the swap label. And at that point, we just got a bunch of nonsense. All right. So if this is happening to you, you go to the source tab, and you just want to make sure that whatever it. Okay, I made my famous mistake again, which is forgetting to save the file first. It's a problem, but it's not a big problem because once I understand it, I just go like, okay, save the file, and then go back and do it one more time. All right, so going back to here, we can now double check, and so we got the code here. So we go to the analysis tab, and then we just go all the way to the end. The stack pointer is back to 0, 0. It is balanced. That's all good. And we did halt with the instruction that we should be halting at. And then the continue execution from in the caller is continuing at location 17. And if I go to the assemble tab, I can tell that 17 as an address is exactly where I should be returning to, because 17 is right here. It is corresponding to the first actual instruction after JMPI to swap. So I know the program is working at this point. So the second thing that I might want to check is what is actually on the stack. So to understand what is on the stack, you have to go to the analysis tab, and then you focus on column C, because column C says we have a 03 at location FE, we have a content of 07 at location FF, and then I proceed to push FF on the stack, and then push FE on the stack. Those are the addresses of Y and X respectively. So I pushed the addresses of Y and X on the stack, and then I push the return address on the stack. And then once I get into the subroutine at location, let's see here. Let's see, when we call the subroutine, we continue execution at okay, I can look up the assemble tab to find out where swap is located. So swap is located at location 1C. Oops, wrong tab here. So we go to location 1C right here. So this is after we return, this is after we continue execution at the subroutine swap. So what the subroutine swap did was to change the stack pointer. So it went from FB to FA because we are allocating for that one extra byte that we need for the local variable. It did absolutely nothing in between, and then the stack pointer became FB again because I deallocated that one byte for the local variable, and then we retrieve what is the last item pushed at that point of time, which is 17 on the stack, then that's my return address. And then after that, we increment the stack pointer because the subroutine is responsible to pop the return address. And then we and then we continue execution in main, and this is the continuation in main. And then in main, we have two increment D in order to deallocate the two arguments sitting on the stack. And then we also have another instruction to deallocate the two local variables on the stack. So two more increment D to deallocate the two local variables. And now the stack pointer is back to 0, 0. So everything is accounted for. Okay, that's the whole point. Is I want to make sure that everything is accounted for looking at the trace of this code. So now that I know everything is good, the stack is set up correctly, I can explain every single item on the stack. I can now write the code corresponding to the C code. So this is not a very sequential or linear process. It is definitely non-sequential because this way, if I do make any mistake, I can catch that mistake early on. So now we need to implement what is on line 4. And to implement that, I need to first figure out what PTR1 is pointing to, which also means I first have to figure out what is PTR1, which also means I first have to figure out where PTR1 is at, which also means I need to know what is the displacement, the number of bytes between where the stack pointer points to and PTR1. Do you see how I'm tracking all that stuff backward? I start with what I need, and then I go backwards and go like, in order to get that, what do I need first? Well, okay, now we have the second step. In order to know that, what do I need next? Da da da. So I just kind of work my way backwards. Okay. So once I work all the way backwards, I can now say, the first thing I need is the offset of PTR1 from where the stack pointer points to. So if you want to comment this, there are two ways to comment this. You can basically say B is the offset to PTR1, which is kind of concise, but it doesn't really say, that it is from where D is pointing to. The other way to comment this particular line, which I think is a little bit more helpful, is this really is the address of PTR1? Not entirely, because you have to subtract the stack pointer from the address of PTR1, because now we're looking at the actual number of bytes between where the stack pointer points to and the address of PTR1. So if you ask me, I would say line 46 is a better description of what register B has at this point, but the first one, or the comment on line 45, is okay. It's a little bit more vague, but it also sort of describes what it is. So do we have any questions about the commenting of line 45 versus line 46? No questions? Okay, all right. So then what we need to do next is to say, well, I have the offset now, but that's not going to help me unless I can somehow use it to figure out the address of PTR1. So when you add the stack pointer to B, then B, okay, if I want to do this really, really step by step, then it becomes PTR1 minus D plus D, right? Because that's what add is going to do, is adding the stack pointer to what we already have in register B, and then you use algebra, and you go like, it looks like minus D plus D are canceling each other out, so we ended up with PTR, the address of PTR1. Cool, but we are not interested in the address of PTR1. It's just a means to an end because we want to get to what PTR1 is pointing to, but we cannot know what PTR1 is pointing to until we get what PTR1 is. So we have the address of PTR1. Now we have PTR1. So B is, technically speaking, we dereference the address of PTR1, and then the asterisk and the ampersand, they cancel out each other. So we basically now we have the value of PTR1. And that is close to what we actually want because we want the byte that is pointed to by PTR1. So that means we need one more dereference at this point. So the B is now finally whatever PTR1 is pointing to. All right, so I'm going to pause because I'm hoping this is like super boring stuff to all of you, because if that is the case, it means you guys are mastering the concepts already. This is just like tech. Please stop talking about the same thing over and over again. That would be a good sign. Okay. Do we have any questions about line 45 to line 49? Because all these lines combined is computing the right-hand side of the assignment on line 4 of the C code. So we good here? All right. So given this is good, now it is time to deal with the left-hand side. So the left-hand side is going to start with LDI. I cannot use register B anymore. I have to use the other two registers. I can use A or C. So I can use A, and now it is swap underscore T, which is the offset to the local variable T. Add AD, now it becomes the address of T, and now I can do a store A, B, like so, like so, to complete the assignment. So that's for line 4. Line 5, kind of the same deal over and over again. So we have PTR2 this time, add BD, LD, BB, LD, BB. That's our right-hand side. And then the left-hand side is going to be a little bit different, not by much, just a little bit compared to the previous line. So now we have the offset, the address, the value of PTR1, and that turns out to be the address that we want to store whatever is on the right-hand side. So that is line 5. And then we get to line 6, which is, I mean, if you are thinking, oh, this is more of about the same thing, well, the answer is yes. We are basically repeating the pattern here. Okay, so we have the address, and then we have the value of local variable t, and then on the left-hand side, we have swap underscore ptr2, add ad, ld, a, st, a, b, and that should do it. All right, so do we have any questions about this code? And as you can see, it is the same pattern kind of repeating over and over again, except sometimes we have an extra LD instruction and other times we do not. And the reason why is because some things are pointers and some things are not pointers. So if you're looking at a pointer and you want to look at what the pointer is pointing to, that's where when we need an extra LD. But on the other hand, if you're just looking at a local variable and the local variable itself is not a pointer, then you don't need, there's no, okay, I shouldn't say you don't need, there would be no extra LD because the extra LD would be incorrect in those cases. All right, so I'm thinking this code is going to work. I mean, I really am not carefully checking it because secretly, I'm hoping this code is not going to work so I can actually show you how to debug this kind of program, which is actually helpful because your homework assignment for the structure thing is due on Thursday. So if I teach you how to debug programs like this, I think it's going to be helpful for people who want to get it done by Thursday. All right, so the program is all done. Now we go to the trace, and now I have to figure out what I'm actually supposed to be looking at. So what I'm supposed to be looking at would be the content at FE and the content of FF to be exchanged. That's what the swap subroutine is supposed to do. So I'm supposed to see FE getting the content of F07 and FF getting the content of 03 somewhere along the line of the execution of this program. So I can scan, I can use the search feature. There are a lot of ways to do it. So this is the first one. FE is now changed to F07, and then now we have FF changed to 03. So the program did what it is supposed to do, but I also want to make sure that not only swap is getting the job done correctly, but it also return correctly so that main is going to terminate correctly. And that turned out to be the case as well because we can see the stack pointer is balanced and we do stop at the halt instruction as intended. So that's the solution of the swap homework assignment. Do we have any questions about this process? Not so much only the code that I showed you, but also the process of getting it done, or the concepts involved in the process to get it done. Okay, so there are no questions. All right. So if there are no questions, I am going to kind of move forward with the exam, the final exam from spring 2022. So I'm very careful not to call it a review or to call it a practice exam. I'm just calling it exactly factually what it is, which is the final exam from spring 2022. In other words, I'm very careful not to imply any type of similarity between what you will be seeing as the exam from spring 22 versus the final exam that you will be seeing as your own final exam. So, just lots of disclaimers. My dad always said that I should be a lawyer, but I don't have the grade to make it to law school, so here I am. I'm just kidding you. I don't want to be a lawyer. All right, so let's go ahead and start with the final exam. So I can do, let me see what I want to do. I think I'll do it this way. So I'm just going to copy the final exam from my other account. And I want to look at, oh, oh, I forgot that one thing in between. It's 1223 fxw that. All right, so we are looking at a text file, and I will copy that to the temp folder as final.ttpasm. All right, cool. I think that should do it. And then we'll take a look at it. Okay, so final.ttpasm, and the same thing again. So I'm basically opening the same file twice in the same editor, and that's because at some point I want you to focus on one side we have the C code, on the other side we will have the assembly code. So the point of the final exam, at least in 2022 spring, is I will give you the C code. Okay, so let me kind of skip forward to the C code first. So this is the beginning of the C code as indicated by line 27. And the C code ends on line 65 or 66. And I will also give you the assembly code. So I'm going to skip forward to the assembly code. And the assembly code starts on line 98. So your job is to figure out what is wrong with the assembly code and fix it. So the assembly code is an attempt to implement the C code, but it contains certain flaws in it. The flaws are intentional, so in other words, I know exactly where the flaws are. Then your job is to find all the flaws and fix them. Okay, is that okay? But does everybody understand what the final exam in spring 22 is about? Get the C code. You don't have to implement the entire thing. I will give you the assembly code that is actually faulty. So your job is to find out what's wrong with the assembly code and fix it and tell me and explain to me, this is wrong because blah, 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 and this is how we fix it. All right. Do we have any questions about the format of the final exam in spring? No questions? So at this point, I think it's a good idea to let you guys know that it's also going to be open book and open notes, which means what I work on today, you can bring that with you. Now, how much is that going to help you? I cannot predict. Okay, to some people, maybe it's super helpful. To some other people, it may not be as helpful. So it's entirely up to you guys to decide what you want to bring with you and how you might want to pre-process the material prior to the exam. So you're not just bringing something that I gave you, you're actually including your own insight, your own comment, and your own annotation before you bring it to the exam. So that part is up to you. So we'll go ahead and look at the C code from the beginning because there are certain things that we need to take care of. So the first one is, how do we define a structure in TTP ASM? The answer is we use the labels, okay? So this part here, and I try my best to be user-friendly, In other words, instead of just giving you a bunch of assembly code with no comment, no correlation with the C code, I try to sprinkle my assembly code with between C code in comments. So this way, it gives you at least some context of what the assembly code is wants to accomplish. So right here we define the struct node here, and the struct node is defined by some labels. The first label is corresponding to the number of bytes of the member p next from the beginning of the structure itself. And because I said in class I said the allocation of members within the structure is sequential based on the order of the members as they appear in the structure definition. So p next being the first member is going to be at the very beginning of the structure itself, and as a result, the offset from the beginning of the structure is going to be 0. Okay? And then value being the next one is based on where p next is, which is the previous member, plus the size of p next. And p next being a pointer only occupies 1 byte in TTP. And then the next label is trying to define what is the number of bytes that we need for each struct node. So that is based on where we find the last member, which is value, and plus the size of that particular member, which is also just 1 byte, because value as a member is also just an 8-bit integer, which is basically just a single byte. So those labels all look good to me. Is that okay so far? So along with explaining the answer to the final exam, I'm also using this opportunity to go over concepts that we have already introduced in this class, and many of those concepts are actually what you need to complete the homework assignment that is due on Thursday. All right, so that looks good to me. And we're now going back to the initial code here. No op, okay, nothing can be wrong with the no op instruction in most cases. So right away we see LDIA.8 plus. Okay, what is that? What is it going? What is going on here? What is it doing? So we have to say, okay, so we have offset 0, offset 1, offset 2, 3, 4, 5, 6, 7. This is 8. So we are really just pushing the address of the halt instruction on the stack. So this is the initialization of the stack pointer. These two instructions together is pushing whatever is in register A, which is the address of halt. Oh, Tech, doesn't that resemble just how we call a subroutine? The answer is yes. We are simply calling main as if it is a normal subroutine in this particular case. Is that okay? So when we get to main, we have to make sure that it does behave like a regular subroutine. It doesn't stop with halt itself because it does want to return to the halt instruction over here. And then the JMPI to main is continuing execution at main. Okay, so that's not too bad. Next, we want to look at the other parts of the C code. So we are looking at line 36, 37, and 38. They are defining 3 initialized global variables named N3, N2, N1. So are there any questions about the actual meaning of these 3 lines in C? We have 3 initialized global variables. Each one is a structure. So I just basically have to use curly braces to indicate in the order of the members what values should go into each member. And that's how you initialize a global variable or any variable that is of a structure type. So we good there? All right, okay. So in the assembly code, okay, we try to match, something equivalent to that, and that would correspond to line 118 all the way to line 128. Basically, I'm just doing exactly the same thing. Okay, the first member is p next. So in terms of n3, that's a null pointer. The second member is the value, so it has a value of 4, which is exactly matching what the C code is trying to do. So I do the same thing with N2 and as well as N1. Global variables are not living on the stack. Global variables are static in the sense that once you allocate it, it just kind of stays put in place. It is not on the stack. Which also means the label N3, N2, N1, they are indeed referring to the addresses of N3, N2, N1 as global variables already. Is that concept okay? Because that concept is also, I think, well, maybe not in this class, but is that concept okay? That global variables are statically allocated. If they are not on the stack, we simply tell the assembler and go like, hey, reserve these bytes over here, get those initialized to these particular values, and then we use labels to help us remember where they are. Are we good so far? All right, okay. So moving on, the first thing the program is implementing is F. So we can go ahead and just analyze F first. But it really helps to be able to look at the function definition in C first. So the function definition in C is starting on line 40. It ends on line 54. And the best thing I think to do first is to really look at the C code and make sure that we understand all the concepts before we proceed to look at the assembly code to implement the same thing. So I'm going to go line by line, structure, construct by construct. So the first thing is, what exactly is the return type of F? This is not a typo. So what is the return type of function F in C? It has two asterisks. So it is a pointer to a struct node. Okay? If you understand what a pointer is, then you already kind of understand what a pointer to a pointer is. Because a pointer is a way to find something. So a pointer to something is a way to find something. That something in return would also tell you give you the instruction of finding the other item. Is that concept okay, or do you want me to explain that a little bit more? The concept is okay. All right. It really is helpful also, to draw a picture if you want to, because you're using a picture and using actual arrows to indicate what is a pointer, where it points to, or what it points to, can also be very helpful in this case. But once we get to the code, assembly code, we can try that. As parameters, it has two. It has ppn as one of the parameters, or the first parameter. ppn, I chose the name ppn because it is a pointer to a node. And that's why the name of the parameter reflects what it is. The second parameter is a pn because it is simply a pointer to a struct node instead of a pointer to a struct node. So are we okay with the types of the two parameters of function f? Very good. So once we get into the function, we can see that we have one local variable called result, and result has the same type as the return type because that's actually what I'm returning at the very end. So it's not surprising that result has the very same type as the return type of the function itself. So now we focus on line 43, which is a conditional statement. The condition of the conditional statement is an OR, and the left-hand side of the OR looks like this. So the question is, what exactly is it checking? How would this condition here be true? So you have to digest each part of the expression and figure out what it is trying to express. The first thing is it depends on ppn, the value of ppn as a parameter. Okay, but it's not checking whether ppn itself is null or not. It is checking what it is pointing to. So that means that we have to dereference ppn first before we can do any checking or any comparison. Once we get to what ppn is pointing to, we have a simple exclamation point, which is logical negation. Logical negation is true if and only if whatever is negating is false. False in C also means it is just 0. So that means exclamation point asterisk ppn is true if and only if whatever ppn is pointing to is a 0, is null, basically. Is that okay? So this part here, what I just explained here, has absolutely nothing to do with assembly language programming. Those are all concepts in CISP310. Now we focus on the right-hand side of the OR. So the right-hand side of the OR looks a little bit hairy. but it's not too hairy as long as you try to kind of look at it one step at a time. So let's take a look. I'm using the text cursor here to kind of divert your attention. So the first thing is, okay, we need to know what is PPN. And once we get to know what PPN is, we dereference it. Once we dereference PPN, what we have is a pointer to a structure, and then we use that pointer to find a structure of type struct node, and then we say, hey, give me the value member, the value of the value member, because I'm going to use it for some comparison. Is that part okay? So to describe the left-hand side of the comparison, we are looking at the value member of a structure that is pointed to by a pointer. That pointer, in return, is pointed to by parameter ppn. Is that okay? It helps to draw a picture, right? So let me draw a picture that you guys can all see, and it's going to be recorded. So this way, people can say, "Oh, okay." We can reference back to just that picture. So that's what you are seeing, and I need to switch to what I should be seeing, and make sure my stylus is still having the right coordinate. Yep, it does. Okay, excellent. So journal, new page after. So what it means, okay, is you have ppn as a parameter. So ppn as a parameter is a pointer. It points to some location. Yep. Oh, because I. Okay, so I need to close this and reopen it because I think it lost the connection already. So give me a second to restart the mirroring. I think it's this one. There we go. All right. So ppn is sitting somewhere in the call frame. It points to a byte somewhere else in memory, and that byte in return, okay, so it's pointing to here, but this thing in return is pointing to a struct node somewhere, and then that struct node somewhere has two members. The first member is p, okay, p next, and then the second member is value. So is that picture helping a little bit? Helping you to kind of visualize what ppn is doing? It points to a location. I don't know where that location is. Well, not yet. But from the perspective of the subroutine, it doesn't care. Okay, it just knows that ppn points to a pointer. That pointer in return points to a struct node, and that struct node structure has two members. The first one is p next, and then the second one is value. So is that helping, or at least does everybody understand the picture itself, what it is trying to represent? All right, very good. Okay, so this is all getting recorded. So that means if you are concerned about not being able to copy everything from the screen to your note, during class, don't worry, because it's all getting recorded onto my laptop. The only way it can be lost is somehow my hard drive, my SSD crashes right after class before I can upload it. There's a chance that can happen, but pretty slim. All right, so we're comparing that against, the second one is easier because we're comparing that against the value member of the structure that is pointed to by Pn. So that one does not have the intermediate pointer sitting somewhere else. Pn itself, as a parameter, is pointing to a structure of the type struct node. And then inside the then statement, this part is easy because it resembles the swap subroutine, right? So we know how to do this part already. The left-hand side is trying to store whatever the right-hand side is to the member p next of a structure that is pointed to by pn. The next line is pretty easy. This line is, technically speaking, this looks exactly the same as one of the lines in the swap subroutine. Okay, so I don't think I need to explain that one. And then this one is even simpler because all we are doing is we are copying the value of a parameter to a local variable. The way we access a parameter and the way we access a local variable are exactly the same because they're both items in the call frame. And once we have the labels defined, we access those items in exactly the same way. The else branch here is kind of it's the slightly more tricky one because it has the recursive call. But to you, you don't have to figure out the algorithm itself. Your job is simply to look at the code that is given to you in C already and make sure that the implementation that is also given to you is correct. So in this case, we're pushing pn on the stack. We're also pushing, what is that? I mean, it looks like it looks like this is totally redundant because you said that asterisk and ampersand cancel out each other. Yes, I said that. But that is only the case if they are at the same, right next to each other at a nesting level. These two are not next to each other from the nesting perspective because the asterisk is being applied to ppn, but the ampersand is applied to the reference of a member of the structure that asterisk ppn is pointing to. So they're not right next to each other, and as a result, they cannot cancel out each other. Okay, so this is actually important. So what are we expected to push in this case? We are supposed to push the address of the member p next of a structure that is pointed to by a pointer that in return is pointed to by ppn as a parameter. That was a long description, um, but that's the best way I can describe it. Yep.
Can you just go over? Wait, actually, is it P next to pointer too?
P next as a member is a pointer as well. But at this point, I don't need to know whether it's a pointer or not because I'm not dereferencing the pointer. I'm actually trying to figure out the address of the member, which is the. I'm trying to figure out the address of the pointer, which turns out to be a member of the structure.
Okay. Wouldn't we not even need the ampersand now because the P next is already like if you don't dereference it, it just returns the address?
Yes, P next by itself is the address of something,
Yeah.
but I don't want that. I want the address of the member. I don't want the value of the member. I want the address of the member.
Okay.
Whether the member itself is a pointer or not is irrelevant in this particular context.
Okay.
It can be a char, it can be a pointer, it can be a pointer to a pointer. It doesn't matter because I just need to know where do I find this member. The type of the member is not of a concern to me. All right, so that's basically what F is supposed to do. So in the C code, in the assembly code, we can now go through the assembly code and check whether it is implementing this correctly or not. All right, so this is the entry point of F. As usual, I use labels to define the offset from where the stack pointer points to after we allocate for all the local variables to each item in the call frame. So in this case, we have result being 0 because result is a local variable. It's the only local variable. So that makes sense because the only local variable has to be what the stack pointer is pointing to after the allocation. So that looks good. LVS is the local variable size, which is just 1 plus the offset to result. That looks good because result is a 1 byte thing. That's what this one is about. ppn is the first parameter. It is at LVS 1 plus. That makes sense too because this one is accounting for the return address that is also in the call frame. Typically, we don't need to define the offset to the return address because we don't need to access it. It's of no value to us, but in any way. And the pn is our second parameter. It is after ppn, so we look at where do we find ppn, and we just add 1 byte because that 1 byte is accounting for the size of ppn. So they all look right to me. And then what we do is we take a look at the way we allocate for local variables. We look at the size of local variables in number of bytes, and we subtract that much from the stack pointer. That looks good. And the way I analyze a program is I would actually jump to the end of this code here to see if I have a matching deallocation at the end. So I jump all the way to the end of the entire subroutine, which is a little bit down. And then I look for that pattern. Yep, we got that pattern here. We're deallocating um, the local variables. And then we have the usual return instruction, which is because at this point, the stack pointer should point to the return address. So I get it back into register B. I increment D to pop the return address, and then we continue execution at where register B is. Looks good to me. So now I know the beginning, the entry point of the subroutine, and also the exit point of the subroutine. They're both correct. So now I can just kind of focus on whatever is in between. So I go back to whatever stuff is in between now. So as a hint, when you work on, if this is the format in which you get your final exam, I would just add a lot of comments. Okay, so just be prepared to write stuff on the exam paper itself, because if I don't write anything, I would have a hard time tracking which variable has what at each particular time. And so anyway, so let's take a look at line 140 and so on. So line 140 is my way of saying, okay, let me be kind to you and tell you what the following lines of assembly code is trying to accomplish in C code. Because without that, it gets a little bit harder. Okay, not impossible, but it gets a lot harder to try to figure out what are you trying to do with these assembly code. Which C code are you trying to do? So this makes it a little bit easier for you guys to figure out. Oh, so this code is trying to accomplish what line 100, what line 43 is trying to do in C code. Okay. All right. So I'm gonna cheat a little bit here, in the sense that I'm not gonna write it down, okay? But it's all getting recorded, so that means you can review the recording, and then you can add all that stuff back, to each line. So line 141 is loading the offset to find ppn into register A. Line 142 is computing the address of ppn. Line 43 is getting the value of ppn, and I'm pushing it through the ALU to see if it is zero. Does that look right to you? In the C code, what are we trying to compare against zero? Look at the C code here. Are we checking whether ppn itself is null, or are we checking what it is pointing to is null or not? We're trying to check what it is pointing to is null or not. But in the assembly code, we are only checking whether ppn itself is null or not. So that means this code has a problem. Okay, it's not right. So how do we fix that problem? What is the problem? So we need to dereference it one more time. Okay, so we can say A is ppn at this point, and that is not how that's not what we want to compare to zero. So you said to dereference it. How do we dereference it?
You do it again, LDA.
A. Yep, exactly. So we say add the following line, which is LDA A. Okay. So now we are actually pushing the value of the thing that ppn is pointing to through the ALU to see whether it's zero or not. Okay. So we got one bug fixed. So now we look at the JCI instruction. Is that the right instruction to see if something is zero or not? Yep. We have done this quite a few times already. All right. So, but if f else is the starting point of the else branch, and f then is corresponding to the beginning of the then branch, is the polarity correct? In other words, if I confirm that whatever ppn points to is null, and I go to the else branch, is that correctly reflecting what the C code is trying to express? No, it's the opposite, right? It's opposite to what the C code is trying to say. So I'm going to have to change that. So I'll just kind of comment here and say change this to the following line. And the following line is JZI to F underscore then. There is a f underscore then, I'll just double check and make sure that there's a f underscore then, which is here. So I'm not trying to be tricky in this case. The f underscore then label truly identifies the then branch that is written in the C code. So that also should be able to help you identify whether it's doing the right thing or not. Okay, so if JCI does not take place because whatever PPN is pointing to is not null, then we have to go to the right-hand side of the disjunction, which is this portion here, which is also kind of the portion that looks kind of hairy, because once again, we are looking at member value of a structure that is pointed to by a pointer. That pointer in return is pointed to by parameter PPN. Okay, so how do we get there? Well, the way we get there, okay, because you have to be mentally understanding the concept first in order to check whether the program is doing it correctly or not. So conceptually, we're looking at this picture here. This is PPN. It points to a pointer. That pointer in return points to a structure. Within that structure is a member called value. I need this content here. This is what I need. So the question is, Tag, how do we get there? Okay, so to make this picture more complete and even more quote unquote confusing, I have to also include some additional stuff. So let me just add this additional stuff using a different color. So what I'm adding here is register D is pointing to a certain location at this point. So whatever is at this location is my local variable. So I need to somehow use register D to get to PPN. From PPN, I get to whatever it points to. From what it points to, I get to the beginning of the structure. From the beginning of the structure, I get to the member of the structure. So I have all of those steps to perform. But it sounds complicated, but each step is not complicated. It's just that you need to know exactly what steps need to take place in what order. That's what programming is about. Okay, that is what programming is all about, is to figure out the sequence to get something done. And in this case, I think the pointers, the arrows, clearly indicate what we need to figure out first, and then we figure out that, right? So let's go ahead and take a look at the code and see whether it is getting the job done correctly. All right, so the code here is the next two lines is using node underscore value, which is the offset from the beginning of a structure to a member value of a node structure. And we're adding that to register A. You go like, so what is in register A? Well, from before, we know register A is what we use for the comparison. So register A has asterisk PPN already. I just didn't want to go through all those steps to recompute it because it's already here. Okay, might as well just use it. That's already in register A. So register A, oh wait, hold on a second here. I know what PPN is. I know what register A has, but what is the type of the thing or the value that is stored in register A at this point? In other words, what is the type of asterisk PPN? Okay, so to answer that question, PPN is a pointer to a struct node. If you dereference it once, you get to a pointer to a struct node, which is basically saying the same thing as, oh, it's just the address of some struct node sitting out there. Hey, if I have the beginning of a struct node already, and I add the offset to a member of a struct node, I get to the address of that member. So that's what the add AB is trying to do. And then once we add, we do a dereference because otherwise A simply contains the address of the member, but not the value of the member. So doing one dereference means we are now getting to the actual value of the member. So I'm just going to add one little comment here to say A is technically this thing here, okay? Because this is going to be useful later on because I need to know what I'm comparing in the CMP instruction later on. Okay, so now I look at this PN, okay, address of, this is actually PN, and we are adding the offset to the beginning of the structure. And then we get to the value of the member of the structure. Looks good to me. Okay, let me double check. So this is the offset, this is the address, this is PN, and this is PN points to value, the address of value, and this is the value of member value of the structure. So looks good to me. And then we have a comparison. We compare B to A. So to compare B to A, it really is important to understand what it is actually doing. Okay, so it helps also if I just say that this is what B has. B is that. So now we are doing a comparison, which is doing the same thing as B minus A, and B minus A is the same thing as PPM points to value minus PM points to value. All right. So you have to go back to the C code and find out, okay, what are we supposed to do again? What are we checking again? So in the C code, we are trying to confirm, okay, to get to the then branch, we are trying to confirm that in this case, register B, excuse me, register A is greater than register B. Okay, so if I want to say register A is greater than register B, it's the same thing as saying register A is register B is less than register A, right? Okay, so the way I do this comparison followed by a JLI is mostly correct because we are trying to confirm to get to the then branch whenever, if and only if B is less than A, and that would, let me double check, B minus A is, okay, I got it flipped, sorry, that was my mistake. So I got this part flipped, that was my bad, because B has this, and then register A has this. Okay, that was my mistake. Okay, now it makes sense. So we are trying to go to, we are trying to get to the then branch if and only if B, which is Pn points to value, is less than A, which is asterisk Ppn points to value. Yeah, that resembles what we want to do. Okay, but there's a problem. Well, the issue has to do with what is the type of value as a member? What is it? It's an unsigned 8-bit integer. In other words, this comparison is the comparison of two unsigned 8-bit integers. So when we're comparing unsigned value, which flag should I use to indicate whether the minuend is less than the subtrahend? So this is going all the way back to binary comparison and all the flags that we talked about. So how many people still remember that discussion? Okay, so there's an easy way to figure out, okay? What is the L flag? I think most people remember what the L flag is. How do we compute the L flag?
It's not, it's exclusive or no code.
It's the sign flag exclusive or with overflow, right? So do you think unsigned comparison would involve the sign flag? Just think about those terms, right? Unsigned comparison involving the sign flag, it doesn't make sense, right? Okay, so that means the L flag is probably the wrong flag to use because to compute the L flag, we need to use the sign flag, and we're talking about unsigned integers. Why would I pay attention to the sign flag when we're dealing with something that is unsigned? Okay, so that crosses out the L flag, which probably crosses out the sign flag also. So how many more flags do we have left? We got 3 left. We got the Z flag. Are we checking for comparing for equality? No. Okay, so the Z flag is probably useless. How about the overflow flag? Do you think the overflow flag is going to be important here? How do we compute the overflow flag itself? We look at the sign flags of the minuend, the subtrahend, and also the difference. So once again, we are looking at the sign flags of stuff when these things are not supposed to be signed. So that means the overflow flag is probably not the right flag to look at either. So out of the 5 flags, which one do we have left?
JC.
The C flag, the carry flag, right? That's what we need to use. But you can see I'm just using the process of elimination here, as per Sherlock Holmes, right? Once you eliminate all the other possibilities, the one that is remaining, no matter how unlikely it seems, has to be the answer. I know I'm probably misquoting Sherlock Holmes, but close enough. So it's the C flag, okay? The C flag is also the borrow flag, which is the flag that we use to indicate whether the minuend is less than the subtrahend in a binary comparison. So I have to fix that. Okay, so we're going to say fix this. It becomes JCI to F underscore then. So all of this stuff here is not intentional comprehensive, or being comprehensive intentionally. It simply just comes with whatever topic that we are dealing with here after the second exam. So you still need to brush up and make sure that you understand the flags correctly. All right? So it's not something that you can just go like, yep, we are done with that. Nope, we are not really done with that. All right, so, and the way we do the branching, the direction, looks right to me. If it is less than, we go to the then portion. If it's not, we go to the else portion. That's all good. So now we get to the then portion. So the first thing I want to check when we get to the then branch is to check for that little kind of jump around thing at the end of the then branch, because you don't want the then branch to continue to the else branch, which is exactly what is happening here. So I'm going to have to branch around the entire else branch. So I need a JMPI to the end of the else branch. So let me go look for the end of the else branch. Okay, that is labeled by F underscore end if. So I need a JMPI to go all the way around to F underscore end if here. So that fixes one problem, and I'm going to say insert the following. So this way I know, this is actually added to the code. It's a fix. All right, so now we're getting to the actual content of the then branch. The first thing we need to do is to do this in C, the line 45. So we have the offset, the address, the actual content. Aha! So we are missing one, the reference here. Add the following. Because we are not interested in copying PPN, we're interested in copying whatever PPN is pointing to. So we need that one extra LDAA. On the left-hand side, we have the offset to PN, the address of PN, PN itself, the offset to a member of the structure that PN is pointing to, and then the address of the address of the member of the structure that PN is pointing to. It's all good, except we're missing something here. What am I missing? I did all the calculations correctly. Register A does end up with whatever is supposed to be on the right-hand side. Register B does end up with the address of whatever is supposed to be on the left-hand side. What does an assignment operation do?
Loads a register.
Hmm?
Loads a register.
It updates. It's supposed to update the left-hand side, right? Am I updating anything? In fact, if I want to update something, anything like a parameter or a local variable, which instruction should I see as an update? What is the only instruction that can change content of memory? Hmm? No. Store, okay? It's the store instruction. I don't have a single store instruction here. And line 177 says, let's start with the next line of code. I think we're missing an ST instruction. But what am I supposed to be storing to what else? Okay, we know a store instruction, right? The first thing has a pair of parentheses, the second one does not. So what do I put inside the parentheses? What is providing the address? Which register has the address of the left-hand side? This is, yeah, go ahead. Register B, that's right. So register B is where we want to store on the left-hand side. So that means register A probably is corresponding to whatever is on the right-hand side. So this is where you really need to follow each line of code and figure out what is in each register at any particular time. Because if without doing that, you wouldn't be able to spot that, oh, we're missing a store instruction, and register B and register A in this particular arrangement is what we need. Is that okay? All right. The next line I'm not going to explain, but I would check, okay, to see whether it's doing it correctly. So we have the offset, we got the address, we got the parameter itself, we got the offset, we got the address. Well, at this point, we got the address of ppn. Do we want to overwrite the parameter itself, or do we want to overwrite what the parameter is pointing to? That's a question. It's one or the other, right? You got a 50-50% chance to guess it correctly. So let me repeat the question. Are we going to overwrite the parameter, or are we supposed to overwrite what the parameter is pointing to? It's like the optometrist asking you that question, A or B? What is pointing to? Very good. And yet the instruction is storing to the parameter itself, so that means I'm missing a dereference. Wait, so if I'm missing a dereference, what would that dereference come in? What is the form of that dereference? Because both LD and ST dereference, they just do slightly different things to what is being dereferenced. So do I need an extra LD or do I need an extra ST? An extra LD, that is correct. So LDBB, that's what I need. Add the following line. Okay, so that's the second line of C code, and this is the last one. All right, so we got the offset. Okay, let me use the pointer to indicate we got the offset, address, the content of ppn. Looks good to me. We got the offset, we got the address, and we are missing something. This is supposed to be an assignment operation. What am I missing here? Something that we spotted earlier also. The store instruction. Very good. So we got all of the things computed, but we're missing that ST instruction to store the right-hand side to whatever the left-hand side has. Very good. So now we are done with the then branch. It's time to move on to the else branch, which is sort of where the fun begins. All right, so we're going to look at line 51 in the C code. So line 51 in the C code is what all of this stuff is trying to implement. So now you need to track a lot of stuff, okay? I would not suggest that you track everything in your head. You definitely want to write it down, okay? In fact, I might make it a point to make you guys write it down in the final exam. Like, the points depend on what you write, okay? Depends on what you tell me about what each register has for each line of code. I might just limit it to a block of code. But to answer this kind of question, you really need to do it to every single line of code. All right, so I'm just going to verbally do it, and you can incorporate what I said verbally into the comment as you get the code to comment on. All right, so we got the offset, we got the address, we got PN, and we push it on the stack. Looks good to me. We got the offset. Oh, and then we got the address. This is not right. Because at this point, we just push something extra on the stack. And as we push something extra on the stack pointer has now been changed. In other words, the stack pointer is no longer pointing to the same place as right after we allocate for the local variable. It is now pointing to one byte below where it used to point to right after we allocate for all the local variables. So let's just try to understand that part. Do we have any questions about what I just said? That a stack pointer, by the time we get to line 206, is actually pointing to one byte below where it used to point to right after we allocate for the local variables. Okay, I see some nodding. Are we all good? So that means I'm actually not correcting calculating the address of PPN anymore because it is supposed to be one byte below where the stack pointer is one is okay, the stack pointer is one less than what it is supposed to be at the point that we allocate for all the local variables. The reason is the reason of that is actually staring at you in the face, because line 203, that extra decrement D, that is why the stack pointer is no longer pointing to the same place as after we just allocate for all the local variable. That one extra decrement D means the stack pointer is pointing to one byte below the assumed location when we created the label. So we need that one plus to compensate for that one extra decrement D that we have in this code. Are we doing okay so far with this? Because to understand this part, you kind of have to understand that the stack pointer is not always static. Okay, we can always decrement and push extra items on the stack. But when we created the label f underscore ppn, we were making the assumption that we are using the stack pointer as if it is pointing to the location right after we allocate for all the local variables. That is the reason why we have the extra one plus at this point of time. All right. So now we got it right. Okay. So we have ppn, the address of ppn, the actual ppn, and then we're trying to add the offset of a member of a structure to register A, but all register A has now is a pointer to a structure. It is not a pointer to a structure. So we need an extra LDA here, LDAA. So add the following line, LDAA. So without me writing out the comment, you can see how difficult it is to follow it. But at least this entire lecture is being recorded. So that means I would definitely review and watch this whole video again to make sure that you can write the comment in to this code here so that you can explain why are we missing that one extra LDAA. So hopefully you can kind of use this as an exercise to truly understand how to implement certain specific code. So at this point, okay, on line 209, A really does contain the address of a structure, and then we just add the offset of a member of that structure to the beginning point of the structure, which means we end up with the address of the member, which is exactly what we need to upload or push on the stack. So we have to say delete the following because this LDAA is not supposed to be there, because we're supposed to push the address of the member, not the value of the member. So that LDAA does not belong there. Is that okay? I mean, in terms of the number of instructions or type of instructions, it's very limited. We're dealing with what? LDI, LDST, add, subtract, decrement, increment, JMP, conditional branches, and so on. So I can count almost all the instructions that we are using in a program like this with both hands. Okay, it's 10 or fewer instructions. It is about the sequencing of the instructions. It is about the connection between what is in a register and associate that with the concept in the C program. That becomes the most crucial part. It is not about the instructions. It is always about what each instruction, what each register has, and what we want to do, and what the code is actually doing. Are we doing okay so far? Okay. Um, I'm trying to determine whether I want to pause here. Okay, let me just finish this call here, and then we'll take a short break. And then when we return, we'll get to main, and then we'll finish up the solution to this entire thing. Okay, so decrement D, we are pushing the address of the member pnext of the structure that is pointed to by a pointer, which in return is pointed to by ppn. So we got that done. And then we push the return address on the stack. So A has the return address, we push it on the stack, we do the recursive call, we clean up the stack because we have two arguments sitting on the stack that are no longer needed, and then we store whatever register A has to F result. So this is the offset, this is the address, and we are storing two result in here. So those are all correct. And then once we get out of the conditional statement altogether, we have to return whatever is in result. So this is the offset to result. This is the address of result. This is copying result into register A, which is the designated register for return value. And then we got to the code that I just analyzed earlier. So that's basically the subroutine F. And let's go ahead and take a short break. 10 minutes, would that be good? Okay. So we'll go ahead and take a short break of 10 minutes, and I can pause the recording, I think. I thought I could, but I'm not sure how to do that. Or I can just let it run for another 10 minutes. So if you're watching the video, by this time, you can just fast forward by 10 minutes. All right, so I'm going to set up a timer for 10 minutes, and then we'll come back here and finish the rest of this code.
I was just saying, I had Sean had a teacher in like the first semester, Dan and I just saw this guy on some teachers.
Yep. I think he's good.
Yeah, and I had like.
Yeah, he's very responsible. Being a part-time instructor, I would say he's more responsible than 70% of full-time instructors.
Yeah, I could name a few professors that.
Yeah, he really tried his best. Yeah, he's not paid much, as a part-time instructor. But he does have a full-time job, which makes it even more interesting that he puts in so much time to his kind of part-time instruction job. Because we have a lot of part-time instructors who has the view of, well, I'm not making a lot of money, I'm not going to put in a lot of effort, I'm just going to do the minimum to keep my job. And Dan definitely goes way beyond that. Yep.
allocate loads of deep reference. It doesn't do it. I need to learn all the rules.
If you go to the opcode table,
Yeah, I'm on
you
that.
have change this back to low
Yeah. So I need to learn all the rules. Like I know eight I would freeze up and deck the outlets, right?
it's like, I just need to complete something.
Technically allocated. Well, no, allocated.
It's like a deck next door.
I just know how to translate this.
Well, I have no idea this one is, but
So,
make up
so Morocco won.
It's actually so cool. Like the
OpenAI.
yes,
all this stuff is
Dude, they play Super
crazy uses for it.
They only lost.
There was a previous one called GPT-3,
Mm-hmm.
but it's paid. Like, and they have a test period or something for the chat one.
Mm-hmm.
Also found the open source one.
Oh, okay.
That's fun. Cool.
So if it's open sourced, do you have to host it, or is it already hosted by somebody?
I think you can actually download the way it's
Host it yourself.
Yes.
Okay.
I used to do that. You know, the Stable Diffusion, the image generator.
Mm-hmm.
I downloaded it and posted it on my computer.
Uh-huh. Does it consume a lot of processing resources?
Yes.
Yeah, I would
The
imagine so.
GPU power.
Yeah, yeah, because I think that one is at least partially neural net based. The way they train the neural net is they have two neural nets. One is trying to become the faker, and then the other one is the fake detector. So the two AIs are basically they try to beat each other. So each one becomes better and better. So the fake detector becomes better at differentiating what is computer generated and what is actually human generated, and then the faker is also at the same time getting better at um, how to fake something, make something that looks real.
Uh-oh.
Yep. You can kind of, yeah.
I'm quite interested in the machine learning.
Sorry.
I'm quite interested in the machine learning. I
Yep.
know there are like different types of the neural.
Mechanisms.
Yes.
Yep. So neural net is only one of them. The problem with neural net is it's really difficult, if possible at all, to extract the knowledge that the AI has learned. Because it's just a black box, right? You poke it in a certain way, it responds in a certain way. Even though it may seem like it's intelligent, but you cannot ask it what it has learned. But there are other learning mechanisms where the knowledge is represented in a way that we can actually interpret. So those are kind of they're interesting. But I think OpenAI is not entirely, at least not entirely neural net based. They also have certain portions that are logic based and also uh, algorithmic based. All right, we still got 3 more minutes. And of course, the depressing part is somebody in one of my classes in 440, discrete structure, which is one of the more difficult classes, before people transfer. And it's probably the way I teach it is also not easy. I mean, I'm not known to be easy. So one of the students, typed the exact question from last semester into OpenAI, and OpenAI answered the question like perfectly, showing all the steps, all the reasoning.
Good to know I'm taking you for the next semester.
And it cannot be stored because all my questions are dynamically generated for each semester, and I change the way I ask the questions every semester. So this cannot be something that is just stored and OpenAI just do the Google search to find the answer. It just figure it out. In other words, okay, if I want to summarize, OpenAI seems to have the same reasoning and problem solving competency as some of my best students, about to transfer to a 4-year university. I mean, specifically to certain problems, obviously, not in general, but specific to programming concepts, math, and stuff like that. It's already there. And then because of Moore's law, by the time you guys get your bachelor's degree, the processing resources and the storage available for AI to exist is going to be at least twice of what we have now.
This is scary.
In a way, it is, but in a way, knowing that first is helpful. It's better than people who have no idea and go like, "Oh, cool! This means I can cheat all my exams." Well, dude, it makes no point to cheat anymore because there'll be no jobs.
I'm curious how the world is gonna change, like the um, the jobs, the degrees, because there is AI.
There are certain types of thinking that I think would be difficult for AI, but I don't think it's impossible. For instance, Albert Einstein, came up with, oh shoot, I just misspelled Albert Einstein. Anyway, so Albert Einstein came up with relativity, and that's novel. That really is novel because it's a different way of looking at time and space. So instead of asking, instead of saying, space is fixed and so, and rigid, he's basically going like, well, I think the speed of light is rigid, and everything else can change to make that a constant. So that's a very important shift of perspective, and I'm not sure, whether AI can do that sort of theorizing or not. I'm guessing it's going to be able to, but it's not something that's readily done, at least not today. But for the daily type of reasoning that the developer has to go through, I think AI is close to it already. So, all right. So it is 10 minutes, and I'm going to get restarted here. The one thing that is kind of interesting is I'm also pretty sure that OpenAI cannot answer questions about TTP because I'm the only person of the entire world using TTP. But as I said, I'm at this point of time, I think cheating is really not um, a major concern anymore because of employer. You have to convince your employers or potential employer in an interview why you are better than the AI. Yeah, so we are looking at an interesting future, and this is going to be a near future too. All right, so here's main, and we'll look at the actual main. So main is not really terribly difficult. It has a local variable. It initializes the local variable to 0, and it just makes 3 function calls to f, and then it returns. So we'll go ahead and take a look at the implementation in assembly code and try to figure out, can we find all the problems? So as usual, I define a label that is supposed to be the displacement or offset, depending on how you want to call that, from where the stack pointer points to where we find the local variable. So since we only have one single local variable, it is both the first and the last of all the local variables. Having an offset of 0 makes sense. Now we have to figure out how many bytes we need to allocate on the stack for the local variables of main. So we have the offset to the local variable and the size of the local variable. We just add those two, and that should be it. But this line actually has a problem. Line 243 is not correct. So why is it not correct? Huh? Missing one? Well, say it one more time. Did you say it's missing one, or did you say it should be one?
It is missing one.
Well, what is it computing instead? It's using node size, it's adding node size and p first. instead of 1 here. So what would be a suggested change? How would you change line 243 to correct the problem that we have on that line? So what you're doing is you're doing a pattern matching, but you may not be actually understanding what is behind that particular pattern. Because what you're trying to do is you're trying to recognize this is how we usually do things. And this one does not do that, and therefore we have a problem. Is that kind of describing your thought process? Okay, so I can only say that it is not effective because it is not correct, not because this is not conforming to the usual pattern. It is not correct because P first is not a struct node. It is a pointer to a struct node. That means if you do have a local variable that is of the type struct node, you do need node underscore size bytes for that local variable. Okay, so it's good that you recognize this does not resemble what we used to see, but the way you describe how to fix it tells me that you're not fully understanding what this particular line is trying to accomplish. So I would definitely try to clarify those concepts of what this one is representing. It is representing the size of the local variable, and all pointers only occupy 1 byte. Node underscore size, on the other hand, is telling you how many bytes is needed by a struct node. So I would definitely make a very clear distinction between of all those concepts. All right, so now we do the allocation. Something is not right here. What do we do when we allocate for some space on the stack? Sub, okay, we are subtracting because we are supposed to be decreasing the stack pointer, not increasing the stack pointer. So at this point, I would also go to the end of main just to make sure that we are deallocating correctly and returning correctly. So I'm skipping all the way to the end of main, and guess what I find? I find that it puts in 0 into A because it's supposed to return 0, and that's it. There's nothing after line 296. So that means this subroutine is missing a bunch of stuff. So first, it's missing the deallocation of the local variables. So I have to use register B and then deallocate all that stuff. So we have main underscore LVS, add that much back to the stack pointer to deallocate. But it's also missing the 3 instructions that are supposed to be here to return to the caller, because this particular main is a regular subroutine. It was called from another piece of code. So we also need LDBD, increment D, and then JMPB here. So I'm going to have to say add all the following lines of code. All right, so with that said, I now can go back to the beginning of the subroutine and try to figure out whether the first line of C code, which is line 59, is done correctly or not. So we got the offset, we got the address, we got the right-hand side, and then we store to the left-hand side. Looks good to me. And then we look at the first call to F. So first call to F requires the address of N1 to be pushed first because that's the second argument. So we load N1 into A, we decrement the stack pointer, and then we store to where the stack pointer is. That looks good. There's no need to add AD in this case because N1 is a global variable. As a global variable, it is statically allocated, which means the label itself is the address of the global variable. It is not relative to where the stack pointer is pointing to. So this code is actually correct. Next, we need to push the address of P first on the stack. And this 1 plus here is correct. For the same reason that I explained earlier, because of this decrement D, the stack pointer is no longer pointing to the lowest memory local variable. It is now pointing to 1 byte below that. And as a result, we need to account for that one extra decrement D with a 1 plus. So that's actually correct. But I'm using LDAA directly over here, and that would not be correct. Okay, I'm pushing A on the stack. So what do I need to do? Okay, there are two things wrong here. One instruction is missing, and one instruction does not belong here. So we'll go ahead and try to figure out the first one first. So after line 256, what do I have in register A? Do I have the address of P first, or do I have the offset to P first? Okay, just like the optometrist, A or B? Do we have the address of P first, or do we have the offset of P first in register A after line 256? We have the offset, okay, which is not the address. We're supposed to push the address. So how do we go from the offset to the address?
You add the original address and then to the offset.
Okay, so when I say the offset, it means the register A is actually the address of what I need, which is P first, minus whatever the stack pointer is. That's the offset, right? So how do I get to the address of P first?
Add AD.
Add AD, very good. Okay, so we need to say add the following line, which is add AD. But since I'm supposed to be pushing the address of P first, not the value of P first, this LDAA does not belong here. So delete this line, and then we can push it on the stack. And then we push the return address on the stack. Looks good. We continue execution at the subroutine. We deallocate the two arguments. I think we are good here. So this is the second call to the subroutine, and you would think, okay, so there should be no surprises here. Well, guess what? I have another way to do the same thing. So this time I copy register D to register C, and then I load N2 to register A. I push register A, which is pushing the address of N2. That looks good to me. And then I load the offset to P first into register A. And this time I add register C to register A instead of adding register D to register A. And this time I also do not have that one extra 1 plus. The question is that correct? Do we have any problem here? So this is where the pattern matching approach is not going to work, because this does not conform to the pattern that I have been using for a long time. And yet, it is actually correct. Because the way it got it done is it took a snapshot of the stack pointer prior to the decrement D. So register C actually has the same value as register D before the decrement D. As a result, I can just add register C to register A when register A has just the offset to P first, and it would actually be able to get the job done correctly. Is that okay? So just pattern matching is not going to be enough. Okay? Because just looking at this code and try to pattern match to patterns that I have been using in the past is not going to be able to say, is this correct or not? Because if you put in extra correction that is not needed, that would be points deducted. Because why? Because I want to know that you know what code is correct and what code is incorrect, and only make correction to the code that is incorrect. I don't want people to say, this is not familiar with me, I'm just going to remove this entire code and replace it with code that I'm familiar with. That is not going to work in this exam. Is that okay? So try not to overlearn, which is a term for neural net training, because once you overlearn, then you will only be able to regurgitate patterns that you have seen as a fixed pattern, but you would not be able to kind of dynamically analyze the code that is actually given to you and figure out whether it is doing what it is supposed to. All right, so this is correct so far. We push the return address, okay, over here, and then we continue execution at the subroutine. We clean up the stack. That looks okay to me. And here's the last part, which is yet another way to do the same thing. So once again, the pattern matching approach is not going to work because what I did this time is I pre-compute the address of P first. So I use LDIC main P first add CD. So by the time I'm done with line 285, I have the address of P first in register C already. I'm not pushing it yet. I'm just saying, yep, that register has what I want to push later on. And then I proceed to push the address of N3 on the stack. And then I proceed to push register C on the stack, which is pre-computed before I made any changes to register D. So as a result of this, this code is also doing it correctly. We are actually just pushing P first, the address of P first on the stack. But does it conform to the pattern that I have been showing you guys? Nope. So then we push the return address on the stack. This is the return address. This is pushing it on the stack. Continue execution at the subroutine. Deallocate the local variables, and we're all done. So that concludes the entire exam from spring 2022. Do we have any questions? So how would you study for this test? Okay, I can tell you what not to do. Cramming everything in the sample and say, I would just memorize every single one of these lines of code. That would not be a productive use of your time. Because one, the exam is open book and open notes. If you say, I want to be able to reference this particular sample program just in case I want to clarify some of the concepts, just print it out, add your own comment, and bring it with you. Okay, there's no reason to memorize anything. Okay, so that would not be a good way to prepare for the test. So how else would you prepare for this test?
Check out your other final exams, see how the layout works. Otherwise, study just assembly.
Okay. How many of you have a photographic memory? In other words, without reviewing the YouTube stuff, you actually remember every single word that I said and everything that I told you about this particular program. Okay, I thought so. So that means one thing you can do is I can actually send you this test here before I made all the changes. So I can give you the original form of this file. So that way you can try to do all of this first by yourself. And then what you do is you watch the video and then you listen to how I explain things. And instead of just going like, I'm listening, I'm understanding what you said, and just think that, okay, and I understand what you said, and therefore I understand the concept. Instead of doing that, pause the video and then write down next to the instruction the what in your own words, okay, what is in a particular register. So it's going to take some time, which is okay. Because remember, for each hour of lecture, you're supposed to spend 2 hours outside of the lecture. That is how I think would be a good use of your time. 3, your focus is not about just memorizing the sequences of instructions. The focus is, what is this C concept here? How do we utilize memory, especially what is on the stack? Once you understand what is on the stack, how memory is utilized, what is pointing to what else, then you try to figure out how to use the TTP-ASM instructions to get the job done. So you kind of have to separate it into all 3 portions. And then the other thing I can also do right now is to check whether this code really is done or not. So are you guys kind of at least interested in checking whether this code is actually done or not, because I might have missed something, and I want to see whether I did miss something or not. Okay. All right. So to check whether the program is working or not, you first have to understand what the C program is supposed to do. So to understand what the C program is supposed to do, we focus on F first. So what F is trying to do is to maintain what we call a linked list. The first thing it does is to change whatever PN, the P next of whatever PN is pointing to be whatever PPN is pointing to. And then whatever PPN is pointing to is what PNB is, and then we just return PPN. So in essence, what it is trying to do is we are trying to insert an item in a linked list. Okay? So the first time you call F, what it is going to do is trying to make P first, this pointer here, that is a local variable of main, to point to N1, and then N1, the P first of N1 in return would point to a null. Okay? When we make the second call, P first would end up pointing to N2, N2 would point to N1. And when we make the third call, P first would point to N3, N3 points to N2, N2 points to N1, and then N1's P next would be pointing to null. So that would be the expected behavior of this program. So I need to look at the C code and see whether it's going to do the same thing or not. And by the way, the C code is compilable in this case, because you guys are going to have a paper test. So that means you don't have all the electronic tools available to you. So the grading is going to be changed accordingly. Because you don't have all the tools, you cannot run TTPSM, you cannot run the C code because it's all paper based. So the grading would actually be reflecting that as well, is because you do not have the tools available to get it to run. So what I'll do is since I now understand what the program is supposed to do, I will go ahead and try to run it. Okay, make sure I save the file first, and this time I did save the file. Very good. So we'll go ahead and say submit, and this one is final.ttpasm. I will be shocked that if it worked the first time that I actually did not. I actually caught all the bugs. We'll see. I don't have a whole lot of confidence of me catching every single mistake because I'm not a very detail-oriented person. All right, so getting back to this code here, we want to look at the assemble tab because I want to know what is supposed to be. Yes, there are a lot of comments here because I want to know what is supposed to be in the structure. So remember what I said. I think P first should point to N3, and then the P next of N3, this byte over here, should point to N2. This byte here of N2 should point to N1, and this 0, 0 should remain here. So that's the speculation of what I expect the program to do. P first is at location FF because it is I take it back. FF is the return address back to the overall code. So FE is the location of P first. So knowing all of that, the first thing I would also check is to make sure the stack is balanced. So I would go to row 479 to make sure that the stack is balanced. So A479, the stack is indeed balanced. Okay, that's not bad. So that means if I did mess up or forget something, it's not disastrous. Okay, so that's good. So the next thing I want to do is to look at the last update to location FE and see what it looks like. This looks okay. So 0C is changed to 0A, and in this tab here, we can see 0C is this one. So this 00 is changed to 0A, which is over here. So N2 ends up pointing to N3. Okay, so that's correct. Okay, so that is actually good. And then we also want to look at the other updates. 0A is 0E. Okay, 0A is 0E. So when we go back to the Assemble tab, 0A is 0E, which is this one over here. So N3 points to N1. So N2 points to N3, N3 points to N1. I keep tapping into the wrong window. And we also want to see what else. Oops, is updated in memory. F7, okay, these are all intermediate stuff on the stack. I am not seeing P first being changed. But we are not changing P first because we're changing what P first is pointing to. All right, so let me go back to the C code and check what it is supposed to do. All right, so we get back to the C code. Oh, okay, I take it back because I think I'm totally doing this incorrectly. This happens only for the non-recursive one. That means when ppn is pointing to a null, this happens, because otherwise it just kind of chains all the way down. Okay, so that kind of makes sense. So it basically looks all the way to the end, and it will only insert at the end. So if it's inserting all the way to the end, that means N1 is the first one, N2 is the second one, N3 is the last one, and P first would end up pointing to the first one, and P first is at location FE. Okay, so now that we know that, we look up column C, and we want to check out how location FE is updated. So FE points to 0C, and that's it. That's the only change. And then we go to the Assemble tab and look at what is at 0C. 0C is at N2. That's not what it's supposed to do, because I think it's supposed to point to N1. And the first call is to N1. So that tells me the first call may not be happening correctly. Just double checking what the code is supposed to do. All right, so how do we check whether it's working correctly or not? So this part does not relate directly to the exam, but it does relate to your homework assignment, because this is how you can check whether your program is working correctly or not. And if it is not working correctly, how do we figure out which part is not working correctly? Your program also has the equivalent C code that would actually be compilable, and you can use online GDB or some other C environment to actually watch how the C code gets the job done. So in this case, in the exam question, my first question is the first call doing its job correctly? And there are two ways to check it too. The first way is to check whether I'm passing the arguments correctly. I'm guessing that I might be missing something with P first, and that's why it's not updated to the address of N1. So we can now check what is indeed updated to the address of N1, because that would give me a pointer as to what the problem is. So N1 is right here, and it has an address of 0E. So the question is, what got updated to 0E in memory? And the way we find that is to change what we are searching for. So we are looking for equals to 0E. And we want a single equal, but we can look through all of this. Okay, so 0A is getting 0E. 0A is N3. So N3 points to N1. But P first is supposed to point to N1 first. So let me go back to the trace and see whether. And that's the only update. All right. Okay, so the question now is, where am I doing this? And this tells you, this is also another feature of the trace analyzer that can help you correct problems, because I think this should not happen. Okay, that's my conjecture at this point. And it happens on line 176. So I can now go back to line 156 and find out where it is corresponding to. So we can now switch back to here, go to line 176, and this is how we updated the pointer, and that doesn't look right to me. All right, so I'm going to fix this code because I don't think it's working correctly, but I could be wrong. We can also put this code in C, into online GDB, and just to figure out what it ends up doing. That will work as well. All right, so we are looking at line 28 to line 64, 28 to 64, write to a new program as final.c. So now I can go to final.c and debug that in C++. Oh, okay. Oh, because I still have all the commenting, it doesn't like it. Okay, change all the comments, get rid of all of those. Oops, undo. Undo. That looks good. Okay. All right, so repeat GCC, GDB final. Put a breakpoint on line 36, just run the entire program, and now we ask what is at P first. P first points to N2, and what is the P next of it? It's P3, and what is the P next of that? It is N1. Okay, so that exactly is what I'm seeing in the assembly code. So the assembly code is actually correct. It's just that I misunderstood my own program and thought that it should do something different. All right, so we're all good actually, because the assembly code does what it is supposed to do. All right, so do we have any questions about how you can, one, go about completing your homework assignment, and two, how to prepare for the final exam? No questions? Well, I'm going to stop the recorder, and you are free to go because I don't have anything specifically planned for today's lab, other than just talking about the exam from last semester. And also, if you have any particular question about your implementation of the program that is due on Thursday, I can also take a look at this time. But otherwise, the lecture itself is over. The recording is finalized. I will get it